cutting it, and you're stuck with either a vague guess or maybe nothing at all?
Exactly. Today, we're diving into one of those scenarios, but there's a twist. We're looking at a really groundbreaking method that cracks open one of these seemingly impossible math puzzles.
That's right. Our deep dive today is all about pushing boundaries, mathematically speaking. We're going to unpack Ezouidi's theorem. It's a, well, pretty revolutionary approach that gives exact symbolic answers to problems people thought were, fundamentally unsolvable or only solvable approximately.
And we're not just talking theory, we're putting it to the test with a real beast, an 18th degree polynomial. Seriously. An equation that, by all traditional rules, shouldn't have an exact algebraic solution. Our mission today is to show you how this theorem systematically takes apart a monster like that, and hopefully lead us all to a bit of an aha moment about tackling tough problems.
Exactly. We'll be looking at the sources, the papers, the formulas themselves,
Yes.
and the solutions that come out. We'll guide you through the logic, showing not just what it does, but how it kind of redraws the map for solving these high degree equations.
It sounds like a journey from no way to wow, elegant.
Precisely.
Okay, so let's set the scene. High degree polynomials. Our listeners know the basics, so we won't rehash polynomial definitions. But what makes a high degree one so tough? And what's the specific monster we're wrestling with today?
Well, high degree polynomials, where x is raised to a high power, say 5 or more, they just get inherently complex. They pop up in modeling really tricky stuff, chaotic systems, cryptography, even quantum mechanics
So
sometimes.
it's not just abstract math homework.
Not at all. They often represent real world systems with lots of interacting parts. And for today, yeah, we're facing a big one, an 18th degree polynomial. It really stretches the limits.
And just so everyone gets a sense of the scale, I won't read the whole thing, it's long, but it starts by 18 minus 18 by 17 plus 153 by 16. And it goes on and on with huge coefficients, finally ending with plus 71 equals 0.
Yeah, just looking at it is intimidating.
Right. So, what makes that equation and others like it so hard for the standard methods we learned?
That's really the core issue. Historically, the main tools were what we call numerical methods. Things like Newton's method, maybe the bisection method. They're powerful for computation, absolutely. But their fundamental limitation is they give approximations. You get a number that's super close, maybe lots of decimal places, but it's still an estimate, not the exact value.
Okay, so close enough versus perfectly right. Why is that difference such a big deal sometimes?
Well, think about fields where tiny errors matter hugely. Designing a microchip, maybe, or in theoretical physics, where the exact nature of a solution could unlock some fundamental truth. Approximations have rounding errors, and with higher degrees, those errors can build up. You lose certainty.
And you also lose the symbolic relationship, like how the roots are related, not just their value.
Exactly. Numerical methods give you numbers, not necessarily the underlying algebraic structure. And then there's this other major hurdle from classical algebra.
Ah, right. The theorem that seemed to say stop trying for exact answers for many of these.
Precisely. That's Abel's theorem, or more accurately, the Abel-Ruffini theorem.
Yeah.
Back in the early 19th century, this was, well, bombshell. It proved there's no general formula using only arithmetic and radicals like square roots, cube roots, to solve polynomial equations of degree 5 or higher.
No general formula. So for many specific equations, like maybe our 18th degree one, it implied you just couldn't write down an exact answer using standard algebra.
That was the takeaway for centuries, yeah. It fundamentally limited what mathematicians thought was possible. It shifted the focus towards approximation or studying properties without finding exact roots. It basically said, for many of these, an exact symbolic answer is off the table using those tools.
Okay, so we've got this massive 18th degree equation. Traditional tools give approximations prone to errors. And a major theorem says finding an exact algebraic solution using radicals is impossible. Sounds pretty bleak.
It does paint a challenging picture.
But this is where Ezouidi's theorem comes in, right? Offering a completely different angle.
Indeed. This is the paradigm shift. Ezouidi's theorem steps in and essentially says, hold on, maybe we've been constrained by those classical assumptions. It directly challenges those limitations, including the perceived barrier from Abel's theorem.
How so? Is it finding a loophole in Abel's theorem?
It's less a loophole and more a different approach altogether. Abel's theorem is about solutions using radicals. Ezouidi's method doesn't necessarily rely solely on radicals in the traditional sense. It uses a different kind of systematic process to find exact symbolic solutions. It's not about approximation at all.
So it's not just a slight improvement, getting a tiny bit closer. It's a fundamental change in philosophy, aiming for and getting the precise answer, bypassing the need for good enough.
That's exactly the philosophical shift. Instead of trying to isolate x using only standard operations and radicals, Ezouidi's theorem transforms the polynomial itself. It looks for hidden structures within the coefficients using a recursive process.
Recursive, meaning it builds on itself step by step.
Yes. It systematically calculates these special symbolic values, peeling back layers to reveal an inherent solvability that classical methods, bound by the constraints Abel identified, might miss.
Okay, this is fascinating. Let's get into the mechanics. We have our 18th degree monster. Classical methods stumble. How does Ezouidi's theorem actually, take it apart?
Right, this is the core of it. We start with that big polynomial, px equals by 18 and so on. Instead of trying to factor it directly, which seems impossible, the method expresses it using a set of, let's call them symbolic coefficients. We can denote them Sk1r.
Symbolic coefficients, like special placeholders the theorem calculates.
Kind of like that, yeah. And the real engine is a specific recursive formula that determines the exact values of these coefficients.
Okay, a recursive formula sounds systematic. Can you break down that formula for us a bit without getting too lost in the symbols?
I'll try. The formula is ASK1R, AGCNR, KKR, ASZ0R, SR1K. Let's unpack the pieces conceptually.
Okay.
First, CNRKR. Those are binomial coefficients, like from expanding A plus BN, Pascal's triangle stuff.
Right, those numbers that pop up.
Yeah. Here, they act like weights, making sure different parts of the polynomial contribute correctly as we transform it. They're part of the structure.
Got it. Structural weights. What about the base terms in there?
Okay, then you have A says 0R, KR. This 0R is the kind of base symbolic coefficient determined during the process. It acts like a foundation. Raising it to the power, KR, scales its influence correctly at each step.
A base value, scaled up. And the last bit, SR1K.
That term, SR1K, refers to earlier coefficients that have already been calculated in the process. That's the recursive part. Each new coefficient depends on the ones calculated before it.
Ah, okay. So it's like building something carefully, piece by piece, where each new piece rests on the previous ones. And doing it this way guarantees it's exact, not just getting closer.
That's the absolute key difference. This isn't numerical iteration getting closer. It's an algebraic reduction process designed to find the exact symbolic values for these ELS coefficients. It uncovers precise algebraic relationships, no approximation involved.
Okay. Now for the payoff. What happens when you apply this meticulous recursive calculation to our specific gnarly 18th degree polynomial? This is the aha moment, right?
This is really where the magic happens with this particular equation. As you run through the recursive process, calculating these coefficients, 7, SAA, R, all the way up to 17, you might expect them all to be complicated expressions.
Yeah, probably involving the original messy coefficients somehow.
But what actually emerges is, well, it's startlingly simple. A truly remarkable pattern.
Don't leave us hanging. What's the pattern?
The calculations reveal that the vast majority of these symbolic coefficients, they just turn out to be 0. Specifically, 0 through F7 and R are all 0. And then skipping 1 RS9 through S16R are also all 0.
Wait, hang on. You're saying almost all of them just vanish? For an 18th degree polynomial, that seems wild.
It is pretty wild. It's not luck. It shows how the theorem can find a deep underlying symmetry or structure hidden in the original equation. And the impact is huge. Our original monster, px equals by 18 by 17 plus 71 just collapses.
Collapses down to what? What's left?
With all those 0 terms gone, it simplifies dramatically to just this. Px by 18r by 9 plus s17r e0, 0.
Wow, okay. That looks much friendlier. 18th degree equation boils down to just 3 terms. That's incredible. It almost looks like a quadratic equation.
You spotted it. That's the crucial insight. It is essentially a quadratic equation, but not an x. It's quadratic in by 9. You can rewrite it as by 9 2, s by 9 plus s17 r 0, 0.
A quadratic in x to the 9. And we definitely know how to solve quadratic equations exactly using the quadratic formula. So what were those non-zero symbolic coefficients that the theorem found? The SAR and the 17R. Were they simple numbers?
They are exact symbolic values derived directly from the original polynomial's coefficients through the process. They turn out to be S8R equals 48619, accounts of 99.
Okay, whoa. That's a big number, but it's exact.
Exactly. And S17R equals 48618 plus 71, S1818. Again, complex looking perhaps, but precise symbolic expressions, no approximations.
Right. So you plug those exact values for S8R and S17R into the quadratic formula for B9.
Correct. And that gives you 2 exact symbolic solutions for the value of by 9.
And once you have the exact values for by 9, getting the roots for x itself is taking the ninth root.
Yes, you take the ninth roots of those two exact symbolic values you found for by 9. Since you're taking ninth roots in the complex plane, each value of by 9 will give you 9 distinct roots for x.
Giving us 18 roots in total, as we'd expect for an 18th degree polynomial.
Exactly. And these roots are expressed precisely, often using complex exponentials, things like e, which capture their exact position in the complex plane. That's the final output. The set of 18 exact symbolic roots. No guesswork, no rounding.
That is genuinely amazing. From this seemingly impossible 18th degree beast, blocked by classical theorems, Ezouidi's method finds a hidden structure, simplifies it drastically to something solvable, and delivers 18 exact symbolic answers. It really does redefine things.
It really does. It shows that the previous limitations weren't necessarily inherent to the polynomials themselves, but maybe inherent to the tools being used. This offers a new tool, a new perspective.
It moves us beyond just settling for good enough approximations in these complex cases.
Absolutely. It provides a pathway to exactness where it was thought impossible.
So, stepping back from the pure math for a second, what are the broader implications? What does this tell us about tackling really hard problems, maybe even outside of mathematics?
Well, I think it's a powerful lesson in questioning assumptions. For centuries, the assumption based on Abel's theorem was that exact solutions of this type were generally out of reach. Ezouidi's theorem forces us to ask, were we asking the right question? Were we using the right framework?
So it encourages critical thinking about accepted limits.
Definitely. It shows that sometimes a radically different approach, maybe one that seems non-intuitive at first, can unlock problems that seem completely intractable within the old ways of thinking. It's about finding the hidden simplicity or structure.
And what does this deep dive mean for you listening right now? You might not be solving 18th degree polynomials over coffee.
Probably not.
But the core idea here resonates, doesn't it?
I think so. Think about any complex challenge you face: work, study, life. This story is a fantastic illustration of not giving up when things look impossible with standard methods. It's about the power of stepping back, looking for a different angle, a systematic way to break it down.
And aiming for the real elegant solution, not just patching things up or settling for close enough.
Exactly. It's that pursuit of the definitive answer, the elegant truth, even when conventional wisdom says you can't get there from here. This shows sometimes you can.
What a ride! From that intimidating wall of numbers and variables down to a solvable form and exact symbolic answers. The big takeaway, the aha moment really, is that there's a systematic way to crack these high degree polynomials wide open, finding precise solutions that bypass those old algebraic and numerical roadblocks.
That's a powerful testament to mathematical innovation. Absolutely. And it leaves us with a really interesting thought to chew on.
Which is?
Well, if these mathematical problems, seen as unsolvable in an exact sense for so long, could be tackled with a fresh perspective. What other areas are out there? In science and engineering, maybe even in social systems. What other impossible challenges are just waiting for their own Ezouidi's theorem, a completely new way of looking at them that reveals a path to an exact, elegant solution?
What established limits are actually just waiting for a deeper dive and a fundamental rethink, something to definitely ponder. Thank you for joining us on this exploration into the truly groundbreaking. We'll catch you next time on The Deep